This video will walk through using Autoscaler with EKS to achieve Fargate scaling simplicity at EC2 prices. The steps for this tutorial are posted at this GitHub repository, and the README file has all the instructions on how to go through this process. So the requirements is you're going to need access to an AWS account. We're going to use an EKS control tool. The link is provided here if you don't have it. And kube control. So the first step is we need to create our EKS cluster. We can do that with this command here. And it'll start to spin up our cluster. It will take approximately 15 minutes for it to be fully initialized, so I'll pause the recording here. And now it looks like our cluster has come up. We can verify that by doing a kube control get nodes. And we can see the nodes are up and ready. The next step is we want to install the Kubernetes dashboard. You can do that by applying this YAML file in this repository. And then in order to access it, you'll need to run kube control proxy, which is a blocking call. So we usually run it in a separate shell. Once we've done that, we should be able to access the dashboard via this URL. Now you should be able to skip the login since you're using kube control proxy. And the dashboard is up and running. The next step is we want to install a couple of example applications. One is CPU intensive and the other is memory intensive. So we just apply these two YAML files in this repository. Now by default they'll come up with 10 pods each. We can verify that by running this command. And we can see that the CPU one is up. The memory intensive one is still coming up. And now they're both up and running, 10 pods each. The next step is we want to configure Autoscaler for this EKS cluster. So you want to log into your Autoscaler account, or if you don't have one, sign up for a free trial. There's a video on how to go through that process. I'm logged in over here, and we want to select Kubernetes Add New. So Kubernetes Add New. Then you select the region and the auto-scaling group name associated with your EKS cluster. Now for instance types, you want to add in a couple of different instance types. Some that are computationally efficient, like the C4 large, and some that are memory efficient, like the R4 large. We'll leave the availability zones as is. And for now, let's turn off the spot parameters, put them to 0. We'll come back to these later. Then you set the spare capacity, both CPU and memory. We'll take the defaults here. And it defaults to the name of the auto-scaling group, but we can give it a more friendly name. Now, Autoscaler runs as a pod inside the Kubernetes cluster so that it can get the metrics that it needs to do the automatic scaling and cost optimization. In order to do that, it needs access to the auto-scaling APIs, which by default are not normally provided through tools like EKS control. So we need to add these to the IAM role for the worker group. You can click here and it should bring up your IAM console if you're logged in. And the simplest thing to do is just search for EKS. And you want to make sure you get the EC2 service-based one. And you can attach that permission however you want. We usually find it simplest to go ahead and attach it to one of these EKS control generated ones so that the cleanup is easier. So I'll select this last one, edit the policy, and add that permission to this statement, which is essentially the describe APIs against the auto scaling. Save those changes, and now I have the appropriate permissions. The next step is to actually deploy Autoscaler to the cluster. You want to pick your Kubernetes version. EKS is currently on 110. And then you download this Autoscaler YAML file. We can pull this file up in an editor and take a look at it. It's essentially a deployment file that captures all the parameters that we've specified so far. In a production deployment, you would want to add this file to your source control. Once we have this file, all we have to do to enable Autoscaler for this cluster is to apply this YAML file. And that's it. We now have Autoscaler configured to manage this Kubernetes cluster. Should take it 20 to 30 seconds for it to come up and register. And we can see it appear here. So for the next step, we're going to scale the CPU and memory deployments and watch how Autoscaler responds. The simplest way to do this is via the Kubernetes dashboard. So I'm going to go back here. Make sure you're on the kube public namespace because that's where these deployments were put. We're currently running 10 pods each, and I'm going to change each one of these to be 13. So let's do the memory one first. You can just click scale up here. Change it from 10 to 13. Now you can watch it here, but kube control is actually a little bit faster. Now we can see that the memory intensive app wants 13 pods. It's actually up to 12. And within just a few seconds, the second one should start. And we're at 13. Now I'll do the same for the CPU intensive application. Scale it to 13. Normally you would do this with a horizontal pod autoscaler, but we're doing it manually for this tutorial. And they're already started and running. Now let's go take a look at what Autoscaler is doing in the background. If you click on the metrics for this cluster, you can see that the target for this cluster is about 11 vCPUs and 32 gigs of memory. So Autoscaler tracks both the active vCPUs as well as the allocated ones and establishes a target for where it tries to drive the cluster to, both for CPU and memory. So we can see with that change, the allocated and the target both went up, but we had enough spare capacity to absorb it, so everything started near instantaneously. But since some of the spare capacity was consumed, it scaled out an instance and is adding a C4 large to the cluster. We can see that by going to the EC2 management console, and we see a new instance now spinning up, being initialized. This process takes 3 to 4 minutes as it spins up and joins the Kubernetes cluster. If you go to the Kubernetes dashboard and select nodes under cluster, you can see when the nodes begin to join in. You can now see this node has joined the cluster. And after about 30 seconds after joining, it'll go to the ready state. Now Autoscaler has driven the cluster back to the desired spare capacity you specified. We can see that in the Autoscaler UI. Notice how the active vCPU and active memory have both raised above the target level. So now, within 5 minutes, the system is ready for another scale out. So let's change it from 13 to 15. The memory intensive one is at all 15. And within just a few seconds, both are running 15 pods. So for the majority of systems we come across, a scaling event every 5 minutes is more than adequate to keep up with the scaling demands of the application, which this process means that you always have that spare capacity to immediately scale. But there's always the case if you get a sudden burst of traffic. What if it's double or triple? What happens then? So let's go through that process now. We're currently at 15. Let's scale both these deployments by a factor of 2. Double them to 30. So let's go to the Autoscaler UI and see what it's doing. So we see a big jump in allocated and target vCPU, which goes above our active, and the same for the memory. Autoscaler detects this and immediately scales out, in this case 4 or 5 instances. We can see that in the EC2 consoles with all these additional instances spinning up. Nice thing about this is it does not matter the scale. If you're going 2 times, 3 times, 10 times, Autoscaler calculates out exactly how many you need and starts them all at the same time. And now you can see we've reached 30 pods for each of the applications in just under 5 minutes. You can see that in the Autoscaler UI as the active resources aligned with the target. So now let's look into the cost of running this cluster. Inside the metrics in Autoscaler, there's a cost tab. So this view shows what it would be using Fargate pricing. Fargate for EKS is not out currently, so this is based upon Fargate for ECS pricing. The green section shows how much better than Fargate pricing we are currently doing. So that corresponds to our savings for this cluster relative to Fargate. It looks to be averaging of roughly 33% so far. This blue band is called an opportunity. So this is the potential additional savings we can do based upon experience, down to this optimal. So there's still some considerable savings left to be achieved here. How do we do that? Well, let's go back to our settings and revisit our spot parameters. This is the simplest way to significantly reduce cost of an EKS cluster. And since Kubernetes does such a good job of replacing pods and moving them around, it makes it very resilient to the rare spot instance losses that do occur. So let's turn this on, put it up to roughly 25%. It's a good idea to never put more in one spot market than your rough value of spare capacity. That means even if you lost an entire spot market, the spare capacity would automatically absorb the loss, and the application or users would not even feel it. And then as far as the percentage of capacity to put into spot, let's put it at 90%. Let's apply these changes and go back to the metric view to watch how Autoscaler responds. So we can see that Autoscaler has triggered 5 or 6 replacements. They're detailed down below. But you can see it's replacing on-demand instances with corresponding spot instances. You can see this occurring inside your EC2 console, where you can see some spot instances are now starting to spin up. After a period of 5 to 10 minutes, the cluster transition should be complete, and it will have moved a significant portion of the compute capacity over to spot for cost savings. Notice how it kept a couple in normal on demand, because that was the specification we gave to only put 90% of the capacity into spot. We can also see this in the Autoscaler UI. We can see a large jump in active capacity as it spun up the spot instances. It did that first ahead to not cause any interruption to the application. It brings up the spot instances, allows Kubernetes to move the pods over to the new instances before terminating the on-demand ones. So the allocated and a target never changed, but we had considerable excess capacity for a few minutes while it did the transition. Same for the memory. If we look at the diversification chart, this actually shows the breakdown between on-demand and the different spot markets. So you can see how we had been running it on-demand, and then at this point in time it diversified into many different spot markets. This is important because it bounds the amount of capacity that's subject to loss at any one time, and by spreading it across multiple spot markets you can limit that impact and keep it below your spare capacity. Now let's look at the cost tab and see what its impact was. So we were running along here. Now that we've introduced some spot, we've dramatically lowered the cost by over 65%, roughly a third of the price of what it would be to be running this in Fargate. So the next step is about dynamic instance type right sizing. So not only does it make sure you have enough nodes to power the cluster and blend in spot instances to lower the cost, it also does dynamic right sizing to make sure the most cost-effective instance type is being used based upon the load characteristics. So we will demonstrate this by changing the relative number of CPU and memory intensive deployment replicas. So we're at 30 now. Let's drop the memory one down to 1. Scaling down is pretty easy. In a matter of seconds, we should be down to only 1 pod for that particular deployment. Now let's watch what Autoscaler does in the background. So notice how the vCPU requirement fell just a little bit, but the memory requirement dropped dramatically. So based upon these new targets, Autoscaler decided it was okay to scale in a little bit. And notice what it picked. It decided that the most expensive resource that it could get rid of and still meet the requirements was a C4 large on demand. This is because now that we're dropping below 10 instances, having 1 normal on demand still meets the 10% requirement, whereas before it required 2. And we also see that reflected in the cost diagram. Now let's do the opposite case. Let's scale the memory back to 30 and the CPU down to 1. And again, let's watch Autoscaler's response. So after a few minutes, we can see the response. We see that the CPU requirements fell way off. Memory requirements returned to just about where they were before. And Autoscaler did several changes. It made a replacement and several removes. If we look at the instance types, and here you can see that it's migrated the cluster completely away from the C4 large in favor of the more memory efficient R4 large blended with the M4 large. Still maintaining the diversification across a blend of on-demand and the appropriate spot markets at a reduced cost. So you can continue to play around with these settings however you like, changing the number of pods on either one of them and watching the response. When you're done, be sure and clean up using the EKS control. Delete the cluster. It will take a few minutes to shut everything down. After about 15 minutes or so, you probably want to check and just make sure it successfully cleaned everything up. That concludes this walkthrough of the Autoscaler for EKS demo.